Hey guys, I'm an intern from SIMMI Foundation and we work towards the benefit of mankind. Current aim is education for all. So what are we waiting for? Let's get started.
Today we shall see what are these atomic orbitals and what is the relation between the quantum numbers. First of all, an atom can have a large number of orbitals. So in our last session we have seen that the wave function and the corresponding energy states gives us the information about the electron, and that wave function is the orbital or the atomic orbital. So the first point about orbitals is that an atom can have a large number of orbitals. Secondly, these orbitals can be distinguished by their size, shape, and orientation. So an orbital of a smaller size means that there is a more chance of finding the electron near the nucleus. Shape and orientation means that there is more probability of finding the electron along certain directions than along the other directions. Atomic orbitals are distinguished by what are known as quantum numbers, and these orbitals are designated by the following quantum numbers, which are n, called as the principal quantum number, L is the isometal quantum number, and m subscript L is the magnetic quantum number, and there is one more called as the magnetic spin quantum number. So moving on to the first quantum number, which is the principal quantum number. It is a positive integer and can have values from 1, 2, 3, and so on. The principal quantum number will determine the size and, to a large extent, the energy of the orbital. So size and energy of the orbital is determined by this principal quantum number. It also identifies the shell, and with the increase in the value of n, the number of allowed orbitals also increases, and it is given as n squared. This is very important. So all the orbitals of a given value of n constitute a single shell of atom and is represented by these following letters. If n is 1, then the corresponding shell is K. If it is 2, then L, 3, then M, and so on. It goes on. The size of an orbital increases with the increase in the principal quantum number. This is a very important point. So orbital size increases if there is increase in the principal quantum number, and the electron will be located far away from the nucleus. Since the energy is required in shifting away the negatively charged electron from the positively charged nucleus, the energy of the orbital will increase with the increased value of n. So orbital size increases with the increase in the number of n, and also the energy of the orbital will also increase with the increase in the value of n. These are the main points regarding the principal quantum number. Moving on to azimuthal quantum number denoted by L. It is also called as orbital angular momentum or subsidiary quantum number. It basically defines the three-dimensional shape of the orbital. So for a given value of n, L can have values ranging from 0 to n minus 1. So it will have possible values ranging from 0 to n minus 1. If we take the value of n is equal to 1, then L, which is n minus 1, will be 0. If we take n is equal to 2, then the possible values can be either 0, and the second possibility can be 1. And if we take it as 3, then there will be 3 possibilities. It can be 0, 1 and 2. Each shell consists of one or more subshells or sublevels, and the number of subshells in a principal shell is equal to the value of n. So the number of subshells is always equal to the value of n in a principal shell. So in the first shell, if n is equal to 1, then there is only one subshell, which is corresponding to L is equal to 0, as we have seen over here. Each subshell is assigned an isometal quantum number denoted by L. Subshells corresponding to different values of L are represented by following symbols. The value for L zero is S. So the subshell notation will be S. For L1, the subshell notation will be P, and so on. We shall look at through this table. So if n is 1, then the possible value of L will be 0, as we have seen. Then the subshell notation it will have as 1s. If it is 2, if n is 2, then it has two possible values, 0 and 1, and the subshell notation can have 2s and 2p, as we have seen over here. And this goes on for value of 3, 4, 5, and so on. The next quantum number is the magnetic orbital quantum number denoted by m subscript L. It gives the information about the spatial orientation of the orbital with respect to the standard set of coordinate axes. So for any subshell, 2L plus 1 defines the value of ml which are possible, m subscript L which are possible. For L is equal to 1, the only permitted value of m subscript L is 0. So if we calculate it using this formula 2L plus 1, we get it as 1. So we will have only one s orbital. For L is equal to 1, we can have minus 1 value for m subscript L, 0 and positive 1. So there will be 3 p orbitals. By using this formula, we will get the answer as 3. So there are 3 p orbitals. This table explain the relationship between the azimuthal quantum number and the magnetic quantum number. So if the value of L is 0, then we will have only one orbital for S subshell. If the value of L is 1, then we will have 3 orbitals for P subshell. So subshell P will have 3 orbitals, and this will go on. Moving on to the last quantum number, which is the electron spin quantum number denoted by m subscript L. So as we all know that an electron spins around its own axis, so it will have a spin angular momentum having two orientations, which are or which have the values of positive 1 by 2 and negative 1 by 2. These are the spin quantum numbers, and they can be denoted as m subscript L. So these are called as two spin states of the electron, and easily they can be represented as arrows. So if an upward arrow is present, then it will be spin up, and if a downward arrow is present, then it will be spin down. So two electrons can have different ms values are said to have opposite spin.
Thank you very much for listening to me patiently, and please stay tuned for more such videos. Once again, Thank you.